Okay, I think the record is on. Now, this is a real problem. We are now going to have the compression member also with a bracing here. So that you see, again, it's the same picture because this bracing goes into the web. So when you look at your, that's too big. When you look at your compression member like this, you now have the bracing somewhere in this direction to cut short the unbraced length in Y direction. Okay, so that means in X direction, again, it is going to be free to rotate with the unbraced length equal to 7.5 meters. But in Y direction, now it would make sense for us to brace our member in the middle, right? Because this seems to me like, okay, this is shorter, this is longer. So that one is going to be the governing unbraced length in the Y direction. But you should understand that from time to time, it's not possible for you to choose because we have the constraint from architectural demands. And you have to believe that they can make your life better because they can make beautiful residential area and so and so. If you are going to be the one who designs the house for yourself, you will end up living in a box because you are too lazy to calculate this and that. Let's put things easily. Yeah, might as well live in a box. So that's the case. And now, you know, this, when we consider the unbraced length in Y direction, this is longer. So if it is going to buckle in Y direction, it is going to buckle here first before it's going to buckle at the L/4, right? So now for buckling in the Y axis, your Ly is now the 5.625 meters. So now we have a problem. We need to consider KL/R in both axes in our design. In X, we have this. So you can enter the table with KL equal to 750. Okay. And, oh, I forgot to do this. It's SS400. And now, oh, because in the old days, I still wanted to demonstrate the LRFD a little bit. So here is given as PU, but your work and your exam, I think we are going to stick to ASD, okay? But when you see PU, somewhere in the future, you would know that this is the LRFD. So from the equation that PU cannot be greater than phi PN. Now we want PN, we can again swap this equation. So PN must be greater than PU divided by phi. Phi is the reduction factor and therefore it should always be less than 1 or not greater than 1. Okay, so here we can have this is going to be 250 over 0.9. See how it increases the load? So your target is now 278 tons. Okay, so we now at the right table, KL 750. This is for x-axis. Okay, and our target is 278. So now we have, remember this is KL over Rx. So you now must look here. Okay, and keep looking in SM400 until you exceed this. So that's where we are. Okay. So you can say, in consideration of the load carrying capacity about the x-axis, you can perhaps try H300 by 300 by 106 kilogram per meter. Okay, because this load clearly exceeds what you want. Okay, with you can also say here that P nominal is 281 tons. Okay, any question about this?
อาจารย์ LY มาจากไหนนะครับ
LY, here, 3/4 of 7.5. So basically, this is 3/4 of 7.5. Okay, it's just the distance shown here. But I didn't do the calculation for you. Okay, and this, to make it clear, it comes from here. Okay. All right. So, but remember, in this case, which is very realistic, you also need to consider the y-axis, and now you have Ly equal to 5.625 meters, or in centimeter is 562.5. Now there's a problem because in developing the tables, I really couldn't go on and develop the KL for every centimeter. So simply put, we don't have the table for this exact length. So what do? We need to try to go over and select the table with the KL perhaps greater than the number that we are going to go for, because we are looking for the capacity for KL equal to 562, right? So if we choose 600, we are choosing the number from more slender information. So we should be safe. We are on the safe side. We are being slightly conservative. Am I correct? Right? We need to look for KL of 562.5 centimeter. So to use KL equal to 600 table, we are on the safe side. Right? Now, this is our target. And remember, this is KL over RY. So we need to keep looking here for SS 400 until we have the load that is greater than our target, which is 278, right? So here we have it. So in considering the buckling in Y direction, we end up with H350 by 350 by 131 kilogram per meter. And look at this guy. When you choose this one, it's larger than what you choose for, KL over RX. But that is the one that we have to go for because it is going to be the one that governs, correct? And P nominal here is 286. You should also see that. No, you shouldn't see. You can't see it until you calculate it because it's two different tables. Okay. So from here, and now we have bigger section from the y-axis. So we are going to try that. Okay. So now once you have picked up your section, you just go to the table and try to pick the relevant information. Okay, that's all. So so it's going to be this one. 350 by 350, that's nominal size, and then 115, right? Notice that the depth is not 350 anymore. The width is not 350 anymore. So when you calculate the ratio, you have to be careful, okay? But again, we have the numbers here. Okay, so going back to our calculation. Oops, wow, not space. So I have to squeeze everything, but we can always add the page, right? So check.
I think it
Yes,
should be
ma'am.
115, but we wrote 131.
Oh, really? Oh, right. Oh, it's a short circuit. My bad. Sorry. Right. It should be 115. Why did I write 131? Maybe I just want to check if you are awake. My bad. I'm sorry. Oh, okay. Thank you very much, ma'am. 115 here, and it should be 115 here as well. Okay, thank you very much. Okay, so you can pick everything from the table. First, oh, I should be this one. Local buckling. Okay, the flange. If I pick the number from the table, it's going to be here 10.9, right? And 27.2. So it is indeed BF over 2TF is 10.9. And now we are beginning to be familiar with the number. We can go ahead and say this is less than 0.56 square root E over Fy, which is 16. And for the web, H over T. Wow, that doesn't look like an H. Let me try again. H over TW, which is 27.2. And now you sort of know automatically that this is less than 1.49 square root E over Fy, which is 42.6. So you can say we get a big okay compact section, no local buckling problem. And now we have the section. Let's see if I can squeeze everything in here. Lateral buckling. Now we check both axes. Again, remember? So you check KL over RX. Maybe if I should be, I should do better job. I should have RX here. It is equal to 15.1. Yes. Please forgive me for the unit, okay? I'm running out of space, but you should always write the unit, you know? Ry, oops, sorry. Ry is here, 8.78. And the gross area is 115. That's weight 146. Okay. The area is there. 146. Okay, so now we're ready to check the slenderness ratio. Now be careful. L in X direction is 750, right? Divided by Rx, which is 15.1. That gives you the slenderness ratio of 49.7. Now in Y direction, it is 562.5 divided by 8.78, which is now 64.1. And you see 49.7 versus 64.1. So sorry, iPad moves. So we can see that this one governs, right? And automatically you should see now that this 64.1 is less than the our limiting value of 4.71 square root E over Fy, which is 135. So you can write somewhere that 64.1 is less than 4.71 square root E over Fy. And you know, you should try to write a square root to cover everything. I was taught when I was in primary school, whenever I don't, you know, draw the line coming down here to indicate that my square root now ends, get a little on the hand. Hey, incomplete. So it becomes quite a good habit. That. And all right. So we go ahead and calculate Fe as usual. Just pi square E divided by KL over R, which is 64.1 and square. This gives us 49. You know what? Let me try to arrange better so that you can see things better. I'm pretty bad at this. Okay. Oh, that looks like a mess now. So this is 64.1, and instead of drawing the arrow, you can just draw a circle instead. Perfect. Okay. And what's this? Drag something with me. Okay. So that's Fe pi square. Okay. So that kilogram per square centimeter. And now we can have our P nominal, which is equal to this. Oops, sorry, I forgot to calculate the F critical. Right. Saturday morning, right? F critical is 0.658 power Fy over Fe 4900, and then multiply by Fy. Seems like we have to intrude a little bit here. So that gives us 2020 kilogram per square centimeter, and therefore we can now have our P nominal, which is this number 2020 multiplied by the area, which is 146. Okay, divided by 1,000. So that gives us 295 tons. And what we want is 280 something, right? Let's go back up. Yeah, 278. So in the end, after we select this, the predicted strength, not predicted nominal strength, I should say, 295. So we are good to go. Okay, so that's it. If you can follow this, if you can understand what we're doing here, you are very good to go, and you can now design compression members. Okay, so is there any question?
Yes.
Yes, ma'am.
How can you know that K is equal to 1 because it doesn't show any kind of support in the drawing?
Oh, right, because I didn't write. Yeah, sorry, my bad. Actually, you must determine, but here it just, I was too casual, sorry. It should be, indicated, oops, in, let's say this is your free body diagram. And when you really design the structure, it is you who determine what kind of support you are going to have, ma'am. Sorry, my bad. Okay. So it's kind of tricky question. You will know because it's you who will make it happen. But if say it's a case where you investigate, it should be given to you then. Okay. For example, one thing I wish to mention from this is this. So is there any more question about this?
No.
Okay. Sorry. Okay, so let us go back here and take a look at this then. Now you know a little bit about compression member. Let's see if you can bring that knowledge to take care of the design of the truss. So we have a little bit here. Okay. Now, the truss. We all know by now that if we design a truss, which is like a simply supported structure, to say the easier word, a simple beam. Okay, now you know that you're gonna have compression on top and tension at the bottom, right? So to say it very easily, your top chord is going to be under compression, right? So now, when we actually fabricate the truss, nobody is going to chop your top chord into pieces so that your assumption of the pin joint in the truss becomes true. The way that the truss is fabricated is that the top chord is always a long member, and then now you don't see it. The diagonal and vertical webs will be attached to it. So when you design the diagonal or vertical web members for either tension or compression, it's pretty clear that the unbraced length, if it's under compression, for these members will be just the member length itself, right? And you can assume this to be pin. So for the web members, K is always 1, and the unbraced length is always its length. Very simple. But when you consider this top chord, now this top chord will buckle in 2 directions as well. Okay, one is the buckling that will move your member in and out of the plane. This you will see from top view. Okay, another, it will move your member, I can say movement is left right. Another is up and down movement when buckling occurs. This one, let us focus here first because it's easier to see. if the buckling will occur in this direction where, you know, your member will buckle up or down like this, the web members will act as you are bracing, correct? Because it cannot move at this joint. So when your top chord under compression is going to buckle in this plane, the vertical plane, the unbraced length will become the length between the joints or the panel, we can say that. Okay? So this becomes your unbraced length in this direction. And now you can say it's a pin, right? So K may be taken as 1. But when I should change the color here so that you can see things, the differentiation of things. Okay. When your compression member here wants to buckle, and so it moves out of this gray plane that you see here. This is the vertical plane, but now it doesn't move in this plane, it moves out of this plane. You can say it's, you can say it's this plane. In the horizontal plane. I don't have anything anymore. Anyway, it's fine. It's now horizontal plane. The web members will not be any help because now your top chord member wants to move on the horizontal plane. So the web can't help now. What can help this member now will be the bracing in the horizontal plane itself where we need to put them. Okay? So let's say if you have the brace coming in here, now it has to be in the horizontal direction, you see? If the brace coming in here, it should help prevent the movement of that top chord in the horizontal plane. So I'm going to try to draw this in 2D to help you see this. So let's say you have the side view of the truss like this, maybe. Okay, whatever. When the buckling is going to occur in this direction, in plane, you see that becomes the unbraced length. Okay, in this plane. But when I look at the truss from top view, you see only the line, right? So this is side view. When you see the truss from top view, you see that if there isn't any bracing, the truss is pretty much free to go. And if you don't do anything, the unbraced length will become the span length of the truss, which is really untenable. We cannot design that. So we will have any, say, bracing coming in. So any brace point will be the point that will help prevent the lateral movement of your top chord in that plane. If we have that, your top chord, because that's a support, right? It may buckle like this. Question, please. This is real. This is how engineers design the truss. the buckling in vertical direction is already helped by the presence of these web members. I can write the note for you. See, side view. Web members help prevent lateral movement. But for this, need something to help prevent. Let's prevent. Let's try again. Awful handwriting. Lateral movement. Okay, but generally, you know, we build the truss to support the purlins, right? The purlins in Thai we call pair, okay? And truss itself becomes a rafter, which in Thai we call jantan. So when you put the purlins on top at each joint, generally the purlins are strong enough to act as your bracings. So luckily, when we have purlins at each point, the purlin will be able to help prevent this as well. So any question on this? Hello? It's too much of a real thing, a little bit, maybe.
ตรงไหนคือแปลกับจันทันอะไรนะครับอาจารย์
Okay. Purlin. That's pair. Rafter. It's jantan. That's it. And in this case, purlin or pair is something that you use to directly support the roof tiles. And the rafter is the one that supports the purlins. All right. It takes some getting used to, and it would be better, you know, if you guys come into the classroom and maybe can bring some trust to the class and show you this better. Anyway, if we don't have any tools to demonstrate this, you're gonna have to try with your imagination first. That's all I have to say. And we have more pictures to try to help this. This is the plan view. You can see that if you look at the main truss like this, you see that's the main truss. It's the plan view will show that if this truss, say it's a main truss, it doesn't support any purlin. The only brace point that this truss is going to have is just coming in where it has the member coming in to help prevent the lateral movement of the top chord. You see, this is the typical truss in this line where it supports purlin. So this is the purlin coming in, and this truss will be fine because it has purlins to help as a brace. But in turn, the green truss here is built to support this yellow truss. So the yellow truss itself becomes a brace point of the green truss. So when you look at this green truss, you see that, let's say, if it's something that looks like this, let's say this is the center line. You see that for the up and down direction, the top chord member can buckle like this, right? But for the in and out of this plane of the iPad, this purple point is where that it is going to serve as the bracing, which is perhaps maybe at this location, that location, then that location. And for buckling in this direction, because now, you know, in this direction, your member will move in and out of the plane entirely, except at this point. So the AIEC say, if I remember correctly, you may use K equal to 0.7. Okay, for that case. But that's a real design. And fortunately, you guys will have the opportunity to do it because we have that in the drawings here. Okay. So before I go in a little bit into the drawings, I would like to have more questions from you if you have any before we move on. Is there any question about the examples? It's straightforward enough, I suppose. Or the behavior of the truss, how we can manage the unbraced length. Don't worry about it if you don't get it, okay? Because let's say this is the first time, your first encounter with the real design of engineering structure. So it is going to take some time for you to get into this, but once you get it, you are ready to design a truss in the real world. Think about that, okay? This is what we do. This is what engineers do. Yes, ma'am.
Can you explain again what is the definition of unbraced length?
Okay. The unbraced length is the length of your compression member between two brace points.
Okay. So the longer the unbraced length doesn't mean that it gives higher deflection.
Here, the longer the unbraced length means that if we are going to use the proper engineering words, your member in that particular unbraced length becomes more slender, correct?
Oh, okay.
Unbraced length is long, is getting longer. Your member becomes more slender, and therefore it becomes more easy to buckle in that respective axis, and therefore the less load carrying capacity. But all in all, we should understand that the load carrying capacity, in this case we mean compression, of your member depends on the unbraced length, not the length of the member. For example, for example, you see from this, let's say this green truss in this picture is 20 meters long. We are not going to design, we are not going to consider the unbraced length in horizontal plane equal to 20 meters if we have the brace point here. The unbraced length that we are going to consider for the strength, compressive strength of the member will be 5 meters. It's not the length of the member, but the length between the brace points.
So in design, we have to design the appropriate unbraced length, right?
It is, yes, right. Because correct. And in fact, it is you who will design the unbraced length. You will select the unbraced length. For example, you may think 5 meters, that's too short. Let's increase it because you can therefore reduce one truss to brace this. So you may want to have 2 brace points, for example, instead of 3. It's your choice, really. And that's design, ladies and gentlemen. It's it's the only freedom you can enjoy, you know, because after that, it's all calculation, right?
Things that give a clearer picture.
Okay, great, great. I always emphasize on the behavior of the structure because, you know, if you understand, if you see the behavior, I coin my own terms. If you can talk to the structure, you know, the calculation will follow. And in other words, if you don't know what's going on, how your structure is going to behave under the load, the calculation will be done like, you know, blindfolded because you don't know where you're going, right? So I think if you ask me, it's important that you understand the behavior first. Calculation is just approximation. Okay, engineering problems are like this. You need to use your knowledge to turn the engineering problems into what I like to call mathematical expression. You understand the behavior, you can explain the behavior in math, and then you solve the math, and then that's it. So the first important thing is to try to bridge the behavior to convert your problem into some kind of mathematical expression. And after that is your math. Okay, and this kind of idea is applicable to any engineering subject. That's what we do. We understand, and so we know the behavior, we have the design model, and then we map the behavior with mathematics. And if you are good at math, the rest is just, you know, simply punching some numbers. Okay. Please, this is the main reason why I like to have the Saturday sessions, because from my rough approximation, maybe one more Saturday, we are fine in terms of lecture. But if you don't spend time discussing with me, and you are fine, you understand the drawings, you understand what you need to do, it's fine. But I'd rather have time with you like this, and then we discuss about the structure so that you really know what you're going to have to do as engineers. Okay. You really hate my hair now. Wow. I have haircut, really. But I hate going to the barber as well. Okay. All right. So more questions, perhaps? Okay. If that's not the case, let us take a look at the drawing for a few minutes, okay, before you go, because your homework / term project will be assigned from these drawings. Forgive me, give the Thai language in the drawings. Okay. This is the school basic plan for the school. Okay, I think Ajahn Sutat did this for her royal patronage project when one of the schools in Chiang Rai had some bad damages after the earthquake. Okay, so the drawings are simple enough. Now I try not to spend a lot of time with this, and I'll see if you get it. If you don't get it, we're gonna spend more time talking about it. Now, I think this is the fun part, you know. If you ask me, when we are going to design something, we look at the drawings, and this is the first floor. It's the opening. It's nothing, and you should know one thing, that when we design something, we are going to design from, say, from up and then down. Okay. But when we construct, it's bottoms up. We're going to have to build the foundation first and then going up. Okay. But in terms of design, you design from up and then down. And when I was your age, when I started off in the design company, I say, okay, the first thing that you need to do when you see the drawings is you mark the columns like this. So that becomes a column. So that you know where you can have your columns going up to support your structure, right? And that becomes the second floor. Just have second floor. Columns are the same. Now, because I think this is a rough drawings and it doesn't contain every information. And please, ladies and gentlemen, keep in mind that when you don't have enough information, you must talk to architects, okay? You just don't say, hey, they don't give me enough information, so I'm just gonna do this right away and assume this and that, okay? From this drawings, you see that they give you two cross-section here. It's a core, cross-section core and cross-section core. Now, these two cross-sections don't give you enough information about what's going on here because the first cross-section look here, and the second look there. So we don't know what's going on in the middle. Okay, now the point is this. You see, there are no columns here. Okay, because it's a corridor and people don't like to have columns in the corridor, right? So no columns. But when you look at the cross section, you don't see the cross section at the corridor. So instead you see this truss, and then you may think, I may have the column to support the truss here. But remember, when you look at the corridor in the drawings, you see, no columns at the corridor. But that cross section looks to the left and then look to the right. So what you see are the columns here that do not go up to the roof level. So that's the importance of the drawings, okay? You guys have done the drawings in your drawings classes, right? Hello?
Yes.
Okay, good. Excellent. So now you can see this too, I hope. So that means in general, when we design this truss, which you will as your whole work, it sounds like fun, right? We don't have this. Instead, your columns are going up from here and then there. Okay, so in fact, if you look at your truss, you have the supports here, and that becomes a cantilever portion. Okay, and that's your truss. I'm not going to ask you to submit this first because we just get going. I want you to spend time trying to understand this. And I think I'm going to start assigning this after next week. This is just the introduction to the drawings. Now, the next thing that you need to understand is that when you see the truss like this is the architectural drawings. So they are not the ones who design the truss. It's you who design the truss. So you don't have to pay attention to what they have here as the configuration. They just draw them to let you know that you can have a truss here, okay? How the truss is going to look like is going to be entirely up to you. So now that means you are going to design the truss by, looking at the date load that the truss has to support, looking at the live load that the truss has to support. Okay, that's the general idea. So where does the date load come from? It comes from the type of roof that you are going to use. Generally speaking, architects will be the one who select the roof type for you. But in this class, we don't have architects. You want to have one? maybe not. If you have your architectural friends in the Department of Architecture, you may want to ask them a little bit about this. If you don't want to do so, please, you will have your freedom to select your own roof. When you have selected the roof, first, you will know how much it weighs. Second, you will know the requirement of the purlins, because when you have the roof, you must arrange your purlins to support the tiles. And each tile will have its own requirement. The spacing of the purlin you need to have, so to speak. So after you select the roof, you will know the weight, the load, and you will know the spacing. So when you know the spacing of the purlins that you need to have to support your tiles, now you know how you can select your truss configuration, because generally your purlins should sit on top of each joint. Right? That is to maintain the assumption that your truss will have the load acting on the joint. Okay. So this is roughly your first assignment, no due date. I don't remember if I have posted the design phase one for you. If not, I would do so shortly today. Okay. But keep in mind that this picture, you see, they don't even draw the purlins on the joint. But again, it's architectural drawings. You don't trust architectural drawings. I mean, not in that sense. It's your responsibility, because people will construct the buildings by using the construction drawings, not architectural drawings. This is just your drawings to give you some idea. So you will have to provide that, the correct construction drawings. Okay, so now go ahead and have fun and try to select the roof. Remember, ladies and gentlemen, if you do this properly, you can keep this as your, say, Bible for design in the future. So please do your own work. Okay, do some research about the roof, pick up the roof that you like, and you will know the load and you know spacing, and then you can select the truss configuration. And the second, live load. Go check the law. I understand that you have some foreign friends in the class, so those of you who are from some other countries, please feel free to use the law in your own country. Okay. Now, ladies and gentlemen, try to study this, and you can try to gather the load. And after you have the load, you can try to assign the load from purlin onto your truss. And if you have done some work, you can come in and, you know, ask me to make some comments on your load and your design criteria before you really have to submit your work. No submission is required as of now. So that means you can afford to do any wild things. You can be wrong, then have me looking at your calculation and stuff. And after that, you know, when you need to submit your work, that work will be graded. But now you have time to do this freely without worrying about it. Okay. But if you don't want to do it now, and then when I ask you to submit the work and then you get the load wrong, that will be punished quite severely, because as engineers, if you use the wrong load to design, that means your structure is in danger, correct? So I would rather hand you some punishment now than, you know, hearing that some of you guys have done something bad in the future. Okay, so Is there any question on this? Oh, all quiet. Wow. This is just for you to start your work. Okay, we are going to do the real things here. We're not going to do just, you know, some problems from the textbook. Hello. So if you ask me, it would be great, you know, if you wonder about this, and then because we have on-site classroom now, you can bring this to discuss with me on site. That would be great benefit for you. Or you can post your questions on Google Classroom and so and so. And I believe that some of your friends have now become friends with me on Facebook. So you can text me directly. You can ask your friends who text me directly. If you do not wish to you know, have direct contact with me for whatever reasons. And of course, you can see before you're gonna do the trust, so you have to put the load on them, and this is going to be the important step. The load that you're going to put on the truss must be correct. You're free to use your hand calculation to calculate the force in truss members, or say use the computer program. Okay. Question, please. Now we are we finished with the compression member with all the examples. You know, next Friday we can start on flexural members right away. Woo! Exciting times.
For this design project, we also have to define the spec of the steel member and also its size and all that.
Yes, ma'am. Of course, ma'am. That's the engineer's job, right? You are going to design the truss, so yeah, you must provide the proper design criteria, the members, the size, and everything. Yes.
So what's the format of this project?
Well, I think I would require you to at least submit your calculation sheet. And I'm not going to go very crazy that you have to draw the AutoCAD for the roof plan. It's a simple sketch will do. You know, because in the real world, I don't know now, because it seems like because our salary is kind of not so much, and you are expected to be able to do everything, including draw the drawings. So, but in my old days, we can simply sketch something and hand it to the drafts people, and they will do it for you. So I'd say, you know, when you submit this, you just try to communicate with me, maybe sketch the truss and let me know what members you use, and you know where the truss is going to be by locating them on. Oh, where's the roof? Excuse me. Oh, where's the roof plan? This one. Yeah, like this. So you may do some, you know, rough sketch, because now we know that you perhaps going to have the, oh, it's not clear enough. You're going to have the columns coming up to support your roof like this. We'll discuss this matter in more details, but now I just want you to gather information about the load first. Okay, no need to design anything. So this is going to be, you know, the rough sketch of your roof plan. Now that these are your columns, right? And perhaps you can just use one type of truss. Because now this one will support the load slightly more than this one, but it's just 1 and 2 on the outer rim. So you may use the same details for quick construction. Okay, and then this becomes your, you can call this like T1, you know, try to be more neat like this. That would be enough, I suppose. Enough to communicate with me, okay? Like this, and then you can say, okay, this is T1, your trust T1, and then you can break this so that okay, we don't see the truss anymore, right? Because that's the roof. That's how you guys draw the drawing, right? And then you're gonna tell me the purlins here, and these are the purlins, okay? You don't have to design the purlin members. You can leave it, but you need to know the spacing, okay? And then after you know the spacing, you know the weight of your roof, you know the live load, you can calculate the point load, you know, which is the reaction of the purlin, right? That will be on your truss here. Remember that the one truss will support the purlin on both sides. So it's like the reaction must be multiplied by 2 on each joint. Don't forget that, okay? Just put your mind to it, and with a little bit of effort, have a lot of discussions with me. You're gonna have a lot of fun. This is real, folks. You will be able to design something for real. Okay. I think as I promised, I would like to take just 2 hours, so that should be enough for today. We are in a good situation in terms of lecture and everything. So more questions, please.
I still like confused about your assignment, right? This one.
I'm not assigning anything yet. You don't have to submit anything. I am simply, let's say, if you want to call it assignment, it's easier to say. Now you are now required to gather information about the load that you would need to use to design the truss. I'm not asking you to submit anything. I'm simply asking you to try to go ahead and gather information about the loading. And when you have some idea, you can bring this and discuss with me either next Friday on site or next Saturday, which we may have another session. Okay. Or maybe Saturday after next.
Okay.
Okay. Just because I understand this is the first time for everyone. So, and I believe that you will not know what you don't know when you haven't done anything. So it is important that you guys get started. You will run into a lot of, unknowns, and you have your curiosity. What is this? What am I going to do with this? So that is when you are you are going to learn. And that is when you're going to have a lot of questions and bring them to me. But now, no need to submit anything, but you should start something. That's like the pain point, because if I don't ask you to submit anything, you're not going to do anything, right? But say this is the opportunity to gather information and discuss first before you actually have to do the real work. Okay. Any question? Keep the questions coming. Ooh, all quiet. You guys must be tired, right? So it's been quiet. So let me stop the record. Otherwise, it becomes too prolonged.